Okay, let's talk about the properties of non-clay minerals. The chemical composition of non-clay minerals determines their hardness, whether or not they have cleavage planes. That controls their resistance to physical or chemical breakdown, and therefore has an effect on how well these particles persist geologically in the environment. Non-clay minerals are generally chemically inert, with the exception of some carbonate and sulfate minerals that are soluble. So you have to be careful if you come across these. The origin of soil is weathering of rock. So if the soil is weathered from the rock and stays right on top of the rock, we call that residual soil, so it's weathered in place. Oftentimes that soil does not stay right on the rock, it becomes transported. And if it's transported from the position of weathering by water, we call it alluvium. If it's deposited by wind, it's aeolian. Deposited in the ocean, it's marine. Deposited in a lake, lacustrine, and so forth. There are other types of geologic formations here too. The constituents of the soil are abundant in the source rock, so they have to be in the rock that's weathering to form these soils. They also have to be fairly resistant to weathering, abrasion, and impact. So if the rock breaks down and the soil immediately just turns into a fine powder or clay minerals, it's not going to weather into a granular non-clay mineral type soil. And the constituents of the soil are weathering products. So they form because rock doesn't stay intact. It forms discontinuities, and it can weather by all sorts of different physical and chemical processes. Let's look at the composition of rocks. Igneous rocks are approximately 60% feldspars. Now this is of course very approximate. The constituents of rock vary from place to place depending on how the rock's formed. But in general we can think of them as being around 60% feldspars, 17% amphiboles and pyroxenes, 12% quartz, 4% micas, and then 8% other sorts of minerals. On the other hand, if we look at the chemical compositions of coarse-grained soils, we find a lot more quartz than feldspars and mica. So the feldspars and mica are really abundant in the parent rock. They are not really abundant in the soil that forms from the parent rock. There's almost no amphiboles and pyroxenes, which are rapidly broken down by weathering. Okay, and that's the reason. Quartz does not have cleavage planes, so it persists very strongly, whereas feldspars and micas tend to break down more quickly into other forms of minerals. The shear strength of coarse-grained soils at low confining pressure is only sort of slightly dependent on chemical composition. There is an effect because the surface roughness depends somewhat on chemical composition. So the shear strength at low confining pressure really depends primarily on particle texture and angularity. And there is an extent to which those features of particles are dependent on mineralogy. So to the extent that they're dependent on mineralogy, the mineralogy does have an impact. For example, the surface texture of feldspar is rougher than the surface texture of quartz. So the friction angle of a feldspathic sand tends to be higher than the friction angle of a quartzitic sand. Mica and feldspar both increase the compressibility of sands. I mentioned feldspar can increase the friction angle. These minerals can form little flexible bridges between soil particles, and when you press on them volumetrically, they tend to bend those bridges and have more compression than minerals that would not have, or non-clay soils, so coarse-grained soils that would not have the mica and feldspar.